Assalamualaikum to Dr. Muhammad Said bin Akub. Today our group from Group 6 will present thermodynamic analysis for subject BMCG 4733 power plant. There are 5 group members for Group 6. First of all, me, Esma Fidos bin Abdul Qasim. Next, Muhammad Akmal Irfan bin Sudarmin. Next, Muhammad Nurakif bin Sulaiman. Next, Muhammad Amar Faiz bin Amiruddin. Lastly, Muhammad Aidil bin Azri. For part 1, the content is what is thermodynamic analysis, importance of thermodynamic analysis, and application of thermodynamic analysis. What is thermodynamic analysis? The study of energy transition and system behavior based on the law of thermodynamic is known as thermodynamic analysis. It entails examining and connection between heat, work, and matters properties. Thermodynamic aspects like enthalpy and entropy, process, state, variable, heat, and work are all is the important element. Importance of thermodynamic analysis: optimizing the design and efficiency of engineering systems, including engines, power plants, and chemical process, requires the use of thermodynamic analysis. It is essential for boosting various technologies' dependability, promoting sustainable practice, and increasing energy efficiency. Research, invention, and education all depend on thermodynamics, which has an influence on everything from environmental engineering to material science. All things considered, it is critical to comprehending and improving energy transformation as well as guaranteeing the reliability and safety of industrial procedure. Application of thermodynamic analysis: first, power generation, optimizing efficiency in power plant; heat engine and refrigeration, enhancing efficiency in engine and cooling system; chemical process, which is optimizing reaction and minimizing waste; next, renewable energy system, which is analyzing and improving performance; next, material science, which is understanding phase transition and material properties; next, automotive and aerospace engineering, which is designing efficient engine and propulsion system; next, manufacturing process, which is optimizing energy use and quality control; and lastly, nuclear engineering, which is analyzing and optimizing nuclear power system. Part 2, example question for thermodynamic analysis. Example question for thermodynamic analysis in condenser. In a steam power plant, steam enters the condenser at a pressure of 0.05 megapascal and a temperature of 150 degrees Celsius. The condenser operates at a pressure of 10 kilopascal. Determine the heat removed in the condenser, assuming it operates under ideal condition. Given the inlet steam condition, pressure 1, which is 0.05 megapascal, and temperature at state 1, which is 150 degrees Celsius, and the condenser pressure, which is pressure 2, is equal to 10 kilopascal. Step 1. Determine the state at inlet, which is state 1, using a steam table to find the H1 and S1, and we will get H1 is equal to 340.49 kJ per kilogram, and for the S1, which is entropy, equal to 1.0910 kJ per kilogram .K. For step 2, determine the state at exit, which is the state 2. Since the process is isobaric, which is P2 is constant, we will find the specific enthalpy H2 and entropy for state 2 at a pressure at state 2. Assuming the steam at the exit is saturated liquid, which is ideal condition, and for H2 is 191.28 kJ per kilogram, and S2 is equal to 0.649 kJ per kilogram .K. Next, for step 3, calculate the heat removed for, which is the Q condenser. Q condenser is equal to H1 minus H2, and we will substitute the value that we get at state 1 and state 2, which is 340.49 kJ per kilogram minus with 191.81 kJ per kilogram, and the final answer is Q condenser equal to 148.68 kJ per kilogram.
So, Assalamualaikum warahmatullahi wabarakatuh. So, my name is Muhammad Akmal Irfan. So, today I am going to present about a sample question related to thermodynamic analysis of fluid. So, the question is: an internal combustion engine operates on a 4-stroke cycle. During the compression stroke, the air-fuel mixture is compressed from an initial state of 100 kPa and the temperature is 300 Kelvin to a final state of 100,000 kPa. The compression ratio is 8:1. The specific heat ratio for the fuel air mixture is 1.4. Determine the final temperature after compression and the work done during this process. So the first thing we have to do is we have to list out all the information gathered from the question. So I list out the initial pressure is 100 kPa, initial temperature is 300 Kelvin, compression ratio is 8:1, specific ratio is 1.4, and the final pressure is 100,000 kPa. So step 1 is conversion of unit. So from P2 is equal to 1000 bar multiplied by 100 kPa per bar. We got 100,000 kPa. So the next step is about the compression ratio. So the equation of compression ratio is Vmax over Vmin equal to V clearance plus V displacement over V clearance. So the question give the compression ratio, which is 8:1. So let's find the V clearance over V displacement. So V clearance over this V displacement, we just substitute 1 into the V clearance and 8 minus 1 to the V displacement, and the answer is 1/7. So we have to go to the next step, which is step 3, ideal gas law. The general equation is P1 V1 powered by specific ratio equal to P2 V2 powered by specific ratio. So let's find V2 over V1. The equation is V2 over V1 equal to P1 over P2 powered by 1 over specific ratio. So we just substitute the value, and then we got 0.767. So after that, we have to go through to the next step, which is we have to find the temperature. So the equation is T2 equal to T1 multiplied by V1 over V2 powered by specific ratio minus 1. So just substitute the value, which is 300 Kelvin into T1 and 0.767 like the answer above, and 1.4 into the specific ratio. So the answer we got is 214.7 Kelvin. So after that, we go through to the step 5, which is we have to find the work done during the compression. So the equation is W equal to P1 V1 minus P2 V2 over specific ratio minus 1. So just substitute the value, 100 into P1, 1 into V1 minus 100,000 subs into P2, and 0.767 into V2 and over 1.4 minus 1. So the final answer of this work done, we got negative 11,425 kilojoule per kg. So the final step is we have to evaluate the result. So from the calculation, we can determine the final temperature of after compression, which is T2 is 214.7 Kelvin, and the work done during the compression on the system is negative 11,425 kilojoule over kg, and the negative sign indicates the work done on the system, and the system is a compression. So that's all from me. Thank you.
Hello, my name is Muhammad Sulaiman. Now I want to present about example question of thermodynamics analysis of feed water heater. The question is, in a system power plant, a feed water heater is employed to heat the condensate before it enters the boiler. The condensate, initially at temperature of 40 degrees Celsius, is heated by extracting steam from the turbine at 3 megapascal and 350 degrees Celsius. The condensate leaves the feed water heater at 150 degrees Celsius. Determine the heat added to the condensate in the feed water heater, assuming it operates under ideal condition. So the given information is inlet temperature of condensate, T inlet is 40 degrees Celsius, steam extraction pressure, P extraction 3 megapascal, steam extraction temperature is 350 degrees Celsius and exit temperature of condensate 150 degrees Celsius. So step 1 is determine the state at extraction. T extraction is 350 degrees Celsius and P extraction is 3 megapascal. So refer to steam table. We find the properties is superheated. So the enthalpy of extraction is 3136 kilojoule per kilogram. And step 2, determine the state at inlet and exit. For temperature inlet is 40 degrees Celsius and enthalpy we get is 135.5 kilojoule per kilogram, and temperature for exit is 150 degrees Celsius. The enthalpy exit is 1929.5 kilojoule per kilogram. So the step 3 is heat added in feed water heater. The formula is Q equal to mass condensate multiplied by hash exit minus hash inlet plus mass steam multiply hash exit minus hash extraction. So we assume mass condensate is 1 kg per second and mass for steam is 0.02. So we put the information into the question and the final answer we get is 1796.87 kilojoule per second.
Hi, my name is Muhammad Aidil Benazri. Now we continue our presentation with thermodynamic analysis of Brayton cycle. This is a sample question about Brayton cycle. A gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. The gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the standard assumption, determine the gas temperature at the exit of the compressor and the turbine to determine the thermal efficiency. From the data given, inlet condition to the compressor, which is temperature 1, is equal to 300 Kelvin, and the inlet condition to the turbine, which is temperature 3, is equal to 1300 Kelvin, and the pressure ratio is equal to 8. For the step 1, determine the state at compressor inlet at the state 1. From the data given, temperature 1 is equal to 300 Kelvin. We can get the value of H1, which is 300.19 kilojoule per kilogram, and pressure ratio 1, which is equal to 1.3860. This value we can get directly from the property table. For step 2, which is determine the state at compressor exit, which is at state 2, is isentropic process. To get the value of pressure ratio 2 is equal to pressure ratio 2 over pressure ratio 1 equal to 8. So to get the pressure ratio 2, 8 need multiplied by pressure ratio 1, and we substitute the value, we can get 11.088. Then we need to find the pressure at state 2 and hash at state 2, and we can get this value by interpolate from the property table, and we get the value of temperature 2 is equal to 539.84 Kelvin. Value of H2 is equal to 544.18 kilojoule per kilogram. Next, for the step 3, determine the state at turbine inlet. From the data given, the temperature 3 is equal to 1300 Kelvin, and we can get the value of H3, pressure ratio 3, directly from the property table. And then for the step 4, determine the state at turbine exit. At the step 4 is isentropic process. So to find the pressure ratio at point 4, we need to use a formula, which is PR3 over PR4 equal to 8. So to get the pressure ratio 4 is equal to pressure ratio 3 divided by 8. We substitute the PR3 value and divide by 8, and we can get 1.36. From the PR4, we can find the value of temperature at state 4, which is 770.25 Kelvin, and the value of H4 is equal to 789.37 kilojoule per kilogram, which is we can get by interpolate from the property table by using the value of pressure ratio 4. For the next question, need to determine the thermal efficiency. We can use the formula, which is W net divided by Q in, or 1 minus Q out divided by Q in. To find Q out equal to H4 minus H1, And after substitute the value, we can get the Q out 489.18 kilojoule per kilogram. For the Q in, the formula is H3 minus H2. And after substitute the value, we can get 851.62 kilojoule per kilogram. Then for the thermal efficiency, which is 1 minus Q out divided by Q in. So we substitute the value and we can get 0.426 or 42.6%.
Now, I would like to explain about the example question for thermodynamic analysis in combustion chamber. The question is, a mixture of methane CH4 and oxygen O2 is burned completely in a combustion chamber. The balanced chemical equation for the combustion reaction is CH4 plus 2O2. It will be CO2 plus 2H2O. If 2 moles of methane are burned under ideal conditions, calculate the heat release during the combustion process. So given the standard enthalpy of formation CH4 equal to negative 74.8, CO2 negative 393.5, H2O negative 285.8. So for this question, step 1, we need to determine the enthalpy change, delta H. As shown on the figure, CO2 plus 2 H2O minus CH4 plus 2 O2. So we just put the value given on the equation. So it will be negative 393.5 plus 2 multiply negative 285.5 minus negative 74.8 plus 2 multiply by 0. So the final answer for enthalpy change delta H, it will be negative 898.3 kilojoule per mole. So step 2, we calculate the heat release Q combustion. For the Q combustion, it will be delta H multiplied by the number of moles burned. So Q combustion equal to negative 898.3, the answer we get before, multiplied by 2, and the final answer it will be negative 1796.6 kilojoule. So for the step 3, we evaluate the result. So the heat released during the combustion of 2 moles of methane under ideal condition is approximately negative 1796.6 kilojoule. So the negative sign indicates an exothermic reaction, and the value represents the heat release to the surrounding during the combustion process. So the final answer for the heat release during the combustion of 2 moles is approximately negative 1796.6 kilojoule.
And lastly, part 3, which is conclusion. To sum up, thermodynamic analysis is a basic and adaptable method used in many different fields of science and engineering. It has an impact on a variety of sectors including environmental engineering and power generation by facilitating the optimizing and understanding of energy related to the process. That's all from us. Thank you.